One last finishing touch on the ANOVA between subjects design is, like in other tests that we've talked about, we can measure the effect size. So it's one thing to know that there's a significant difference between the means, but the question is that a significant effect size? How large an effect size is it? So effect size in ANOVA is measured differently than we've seen in previous tests that we've done. There's several methods to do it, and there's really no standard used, but the most common is called eta squared, and it's calculated using technology. And again, SPSS will report this for you. And it's interpreted in a very similar way to R squared, or the coefficient of determination. And it's the percent of variability in the dependent variable that can be explained by the treatment variable. And again, it's usually expressed as a percentage. So for example, if eta squared is equal to 0.21, then we write that as a percentage, 21%. So as an example, 21% of the variability in how long employees say they will stay with their company can be accounted for by the perceived stress of the experience. So dependent variable is, in this case, would be how long they would stay, and then explanatory variable would be their perceived stress. How do we interpret the effect size? Well, if eta comes out between 0.01 and 0.09, then it's a small effect. Between 0.10 and 0.25, it's a medium effect. And if it's greater than 0.25, then it's considered a large effect. All right, let's move on to the second kind of ANOVA. And a second kind of ANOVA is the one-way within subjects design. And you see this much less often, but I'm going to cover it in case you do run into it in reading the research. So in this design, you have one set of subjects, and each subject is measured more than 2 times. It's the same participants in each group. And you're going to have more than 2 groups because it's an ANOVA. Otherwise, you'd be doing a paired t-test. Okay, so it's also called a repeated measures design because you're repeatedly measuring the same people. As before, the null hypothesis is there's no difference in the population means, and the alternative is at least one of the means is different. And the assumptions are the same as before, but the calculation of the test statistic is slightly different. And this slide explains how the test statistic is calculated. So I'll leave it to you if you're interested in looking at how the test statistic is computed in this case. All right. But essentially, the denominator is removed from the test statistic. So before you saw it was a ratio of 2 different variances, and now you have no denominator when you're computing this test statistic. Okay, so let's do an example. So researchers wanted to determine the effectiveness of 3 types of anti-smoking ads on teens. So each teen was shown 3 ads. So each subject, each teenager in the study, got to see 3 different ads. One with no cues, just words. One with generic cues, in other words, a generic abstract picture. And one with smoking-related cues, a picture of a teen smoking and coughing. Subjects were asked to rate the effectiveness of each ad on a scale of 1 to 7, 1 being not at all effective and 7 being very effective. And the question is there a significant difference in the effectiveness of the types of ads? So in this case, here we have person A, teenager A, and we see 3 scores for this teenager. Teenager B, 3 scores for this teenager. And again, these are the different ad types. So probably generic. The first one was no cues. So let's relabel this. So no cues, generic, and smoking cues. And again, each person was asked to rate how effective they thought this ad was in influencing teens not to smoke. So for example, teen A thought no cues was rated very low, but the other 2 rated more the same and also higher on the scale. Teen B rated no cues the lowest, also rated these two similarly, but had smoking as the most effective. Okay, so let's take a look at the test. So the null hypothesis is that the mean ratings for each ad do not vary in the population. And the second one is the mean ratings for each ad do vary in the population. In other words, there's another way of saying that would be the mean rating for the 3 different types of ads would be the same. And the alternative could be the mean ratings for at least one of the ads is different than the others. So that would be another way of putting the set of hypotheses. Now, using technology, the F statistic turned out to be 17.30, and that gave us a p-value that was very small, less than 0.01. So one of the things I should mention is that the degrees of freedom in the between subjects, within subjects ANOVA is calculated differently. There's only one degree of freedom in this study design. And the way you find this degree of freedom is it's n minus k, where n is the total number of observations, and k is the number of groups. So for this study, we have 1, 2, 3, 4, 5, 6, 7 teens, and they were each giving 3 ratings. So n is 21. And k is the number of categories, so k would be equal to 3. So the degrees of freedom would be 21 minus 3, or in other words, 18. Okay? All right. So if we were going to write that conclusion in APA format, let's go back to our APA format. So it's conclusion. And then we have our F with our degrees of freedom. And then we have our p-value. So in this case, we would say something like the mean rating. So we are rejecting our null hypothesis because our p-value is so small. So the mean ratings do differ. Depending on the type of ad. So that's my conclusion. And I would say my F statistic with, I think we said 18. Let's just check. Yeah. With 18 degrees of freedom was 17.30, and my p-value was less than 0.01. So that's one way we could write the APA in APA format, the results of that hypothesis test.